So this subject, as I say, has had a bit of a checkered history. Here's somebody that was involved. He's Patrick Murphy. He was a so-called astrometeorologist. He predicted the weather on the state of the sun and the stars and the planets. He's an Irishman, so you can see the British press in great good taste has portrayed him as a potato. They've given him a weathercock and an umbrella and all the rest of it, and you can see he's obviously a ridiculous person. The last laugh was with him, of course, because not only did he predict the weather rather badly, but he was predicting all sorts of other things in his almanacs that he wrote every year. And one year he predicted that Prince Albert would be ill, and that year Prince Albert actually died. So after that, his almanacs sold very well. But there was a whole sort of load of people doing this sort of astrometeorology business at the time, and they were considered to be a bit ludicrous. Much more recently, some of you may have seen this film that appeared on Channel 4 a few years ago. It's called The Great Global Warming Swindle. The swindle is being put on the British public by climate scientists who are saying that global warming is due to greenhouse gases, whereas in fact global warming is all due to the sun, according to this programme, which was wonderful in the sense of the graphics and the little particles that were zapping around all over the place. It was great entertainment, scientifically not so good. But there's a certain industry in wanting the sun to be causing global warming. It's natural, say the experts in an article in the Daily Mail. They had a great list of experts who said that global warming is natural. I was on that list. In fact, they'd listed every single scientist who'd ever written a paper to do with the sun and the climate. They didn't care what the conclusions were. And here's another one. This is a good one. There was a paper published about there being more icebergs in the North Atlantic as the sun got got less active at the beginning of the 19th century. No, getting the centuries wrong. This was portrayed in this website here as "Did Sunspots Sink the Titanic?" and wonderful graphics here. So very entertaining, but ludicrous again. And finally, right up to date, we have Boris Johnson, who noticed it was a cold winter. He said to call it warming is obviously to strain the language, and it's time for the government to take seriously the possibility that solar changes are causing climate change, because he'd heard from somebody that the sun was less active recently. So lots of people are interested in this. And of course, this is the context. This is a collection of records of global average surface temperature of the Earth. Now, of course, there weren't instrumental records going back this far. You see, it goes back over 1,000 years. And each of the coloured records is a different person's estimate of what the temperature's been doing over that time, using proxy records, that's cosmogenic isotopes in ice cores and tree rings and this sort of thing, which gives some sort of representation of what the temperature was when those things were created. And you can see that there's a general sort of flat or downward trend of the temperature to about 1850 or so, and then there's a sharp increase in all the records, as well as in this black curve here, which is the instrumental record. So this is what's referred to as global warming, and the question is, to what extent does that warming at the end, or indeed any of those variations, can we put down to behaviour on the sun? That's the instrumental record in a little bit more detail, and you can see this rising temperature, but of course it's not rising all the time smoothly. It's wiggling around all over the place, because this is a wonderful non-linear system, the climate system. It's got all sorts of things going in it, but you can see the upward trend is continuing. But back to the media again. This is referring to a sort of composite of global warming due to greenhouse gases and possible cooling due to the sun. So the paper on the left was published, was a report in New Scientist, I can't actually read it now, I think 2006 or something, a few years ago. And there'd been some scientists publishing a paper that said the sun was getting less active, and if the sun was putting out less energy, would that cool the planet enough, the Earth planet enough, to compensate for global warming due to greenhouse gases? Perfectly reasonable hypothesis, and one that needs testing. Very recently, just last week, you can see a report there from the Daily Mail. The next big freeze could last 250 years. Experts say sun activity wanes every 200 years, which it does. And these Russian scientists were saying that the sun may be entering a new minimum period. And again, that's similar to the article on the left. Perhaps this will counteract to some extent global warming, and we need to know what it's actually doing. So the questions I'm going to ask today are: does the sun's energy output vary? Is there any evidence for a solar influence on climate? Is the sun responsible for global warming? And if there are any solar signals in climate, you can see that I think that there are, can we explain where they come from? So looking at the solar variations, and this is not quite the same thing. So when I'm talking about variability of the sun, I'm talking about, actual changes in the energy output of the sun. This is something a bit different. This is changes in the energy, solar energy reaching the Earth, but due to the changes in the orbit of the Earth around the sun. So there's various parameters that determine the shape of the orbit, and also, of course, we have the tilt of the Earth's axis. You can see over here, with the North Pole, one pole towards and one pole away from the sun at any one time, which of course leads us to the seasons. And this here is a plot of the total irradiance at the top of solar irradiance at the top of the atmosphere as a function of time of year and on the bottom, and latitude up the side. So of course we have the annual cycle, which is going from winter to summer to winter again, opposite in the two hemispheres. And the tilt of the axis will make this more or less extreme, the difference between winter and summer. Then we have the ellipticity of the orbit. So it's not a circular orbit, it's an elliptical orbit, and it can get more or less elliptical, which is measured by the eccentricity over here. And this is believed to be at least partially responsible for ice ages. So what we've got along the bottom here is temperatures taken from an ice core, and you can see the scale is in hundreds of thousands of years, and there's these warm periods with interglacial periods, and then glacial periods with cold temperatures in between. And the time scale is rather similar to the time scale of the variations in the eccentricity or ellipticity of the Earth's orbit. So it's not fully understood, but it's believed that these are related. Now you might wonder why, given that these whole things are varying very slowly, and you might expect sort of harmonic variations, why this temperature is increasing very sharply here and then sort of declining slowly. And it's believed to be related to this seasonal pattern. Because if you get a cold period and the ice grows at the winter pole and gets to such a thickness or such a state that it can't be melted over the summer, then as it's bright when the summer comes, it reflecting the solar radiation back to space subsequently, and then you get a build-up of the ice that can't be compensated seasonally. So you get a very sharp build-up of the ice when it happens. So as I say, that's not to do with the changes in variability of the sun, but it is an indication that changes in solar irradiance are affecting the climate on very long time scales. But these are very long time scales. They're hundreds of thousands of years. They last 100 years or so, which is to do with global warming. So is the sun variable? Here we are. Here's one on very, very short time scale. This is a picture of some solar flares. Now, if you were actually looking at the sun, it would be the size of this white circle here. But on this particular satellite instrument, we have an occluding disk, which is this black thing here, which is covering up the brightest part of the sun so that you can see the flares. And if we look at this little movie, you can see how enormously variable the sun is. It's puffing out these great clouds of particles, plasma, into the space. And this is happening all the time, and you can see the time scale down there with the hours ticking away. So on very short time scales, the sun is very variable. And we can look at some other examples of that in the next picture. So this is actually an amazing picture of the sun's surface showing magnetic field lines, and you can see that particles going around these field lines and little puffs of plasma coming out of the surface of the sun. So it's a hugely variable object, and this is on very, very small, well, I'll say very small scales. That's the size of the Earth there, but small scales for the sun. And this black thing here is a sunspot, and you can see these, I'll get it going again, these little convection cells on the surface of the sun. They're bubbling away all the time. So it's a hugely sort of dynamic body. But one of the most obvious facets of the solar variability that we see from Earth is sunspots. So here's an example of sunspots back in March 2001. And people have been looking at and observing sunspots for hundreds of years. The ancient Chinese have records of sunspots. And so we know that there's something that's referred to as the 11-year cycle. It's not exactly 11 years, it varies between about 9 years and 13 years. You can see a recent record of sunspots on the top graph there. And you can see it's not only variable in length, but it's also variable in amplitude. And we can look at some examples of sunspots. This is January 2009, which you can see is the most recent solar minimum. And this is what the sun was doing yesterday. It's got a few spots now. We're coming up here to what looks like it's going to be a rather weak solar maximum, a rather interesting one, because it's following a very long and extended solar cycle here with a very low minimum. So this is part of the whole picture where the solar physicists are thinking is perhaps we're going into another sort of long-term low activity state of the sun. So the sunspots have been observed, but they're not actually telling you anything about the energy coming out of the sun. What we want, the energy coming out of the sun, is irradiance. But going back in time, we haven't got measures of irradiance, but we have got measures of all sorts of other things. So here's the sunspot numbers, and you can see the little 11-year cycles coming and going back to here. At the end of the 17th century, there's something which is referred to as the Maunder minimum in sunspots. And it's thought that that is not due to the fact that people didn't observe them or weren't looking. They were looking, they'd known about them, they'd been observing them before that, but they were trying to see them and there just weren't any there. And so that's the last grand minimum, the big minimum of the sun that's happened. And we think there might be another grand minimum coming in perhaps 50 to 100 years. So that's interesting on what that means for the climate. There's various other estimates of solar activity. Here's, you can count the numbers of aurorae, which is recorded here. Or you can count the effects of cosmic rays. So cosmic rays are particles that are coming in from galaxies, light years away, and coming through the atmosphere and creating particles, including neutrons. So you can count the neutrons. And the cosmic rays are affected by solar activity, because when the sun is more active, it has a big, strong magnetic field, and it keeps some of the cosmic rays out. So the number of cosmic rays, or the number of neutrons, is inversely related. It's going the other way. There's more neutrons when the sun's less active. So you'll see this scale is upside down. And here's a cosmogenic isotope, beryllium-10, again upside down. It's another measure of solar activity. So we have all these indicators of activity, but what we really want for the energy is the irradiance, and that's shown on the plot up here. And you can see that it's not a very long record, because you can really only accurately measure total solar irradiance from outside the Earth's atmosphere, so after the advent of satellites. And here's a construction of all known measurements of solar irradiance, total solar irradiance, TSI, from satellites. And each coloured curve is a record from a different instrument. So they go back to about 1978, and you can see that when they started, there were sort of two instruments here that were disagreeing by about a factor of 5 watts per square metre in 1370 or so watts per square metre. But they show this behaviour which is similar, with a curving up and down. As we get into the 1980s, we find that all the instruments seem to be agreeing, and again they're all showing this modulation which is reflecting the solar cycle. But then in 2003, this satellite called SOURCE was launched, and it's coming in now, again, another 4 or 5 watts per square metre lower than the other contemporaneous satellites. And this was quite a shock, and of course there's been a lot of discussion about this. And it's been a wonderful example of scientific cooperation, where the scientists involved in each of those satellite instruments, they all got together, they had a long meeting, they discussed their instruments, they discussed the stray light, where it could have come from, why they might have got extra, why they might have lost some. And in the end, they all decided that in fact this low value is right. So we now know that the solar, we used to be called the solar constant, is actually 5 watts per square metre, at least that, lower than what we have been thinking it was for many years, and also actually what's been used in climate models. That's quite intriguing. But you can composite these to make variability like this. So if you put them all onto the same absolute level, then we can see that the variation in solar activity over the 11-year cycle is about 1 watt per square metre, or about 1/10 of 1%. So this is, I better speed up because I'm going to run out of time, but this is just to show that we need continuity in these TSI records, obviously, to be able to say anything about long-term trends. I've talked about the 11-year cycle, but you can see here there's a slight suggestion of an underlying downward trend, which is very, very small and difficult to detect. So what we need is more of these overlapping satellite instruments to make sure that we get the proper trend. This is a picture of all the satellite instruments that were planned, but unfortunately this one, the Glory here, that's not a picture of it blowing up, that's a picture of it actually being launched, but it did blow up subsequently, and so there's a big gap in the records, which is not going to help. So if we want to go back in time, we want to try and think what the TSI was in history. There's quite an engagement in that. So if you know what it's doing now, you can relate it to the proxy measures we got now, like beryllium-10 or carbon-14, and then you can use those proxy measures to go back in time and deduce what you think the irradiance might have been. And here's some estimates of doing that, and you can see that they're quite uncertain, but they're all sort of fairly much agreed about this Maunder minimum period here, and you can see that it's considerably lower than at present. Now this is in units of radiative forcing, which for reasons I could go into, but I won't because I haven't really got time, are about a factor of 6 smaller than total solar irradiance. So it's a few watts per square metre lower at the Maunder minimum than it is today. Now we can look at contributions to the temperature record from different factors. So if we know the solar one, and here's some examples of the solar one in pink and green and orange coming along here, what they contribute to the temperature. So we know something about the energy input to the Earth from those sources. And we know something about the effects of volcanoes. So the blue spikes down here represent the effects of volcanoes. So when you get a big eruption, it chucks out a lot of dust into the atmosphere, reflects a lot of solar radiation away, and cools the climate. So that's the estimates of the effects of those on the temperature. And this big one up here is the effect of greenhouse gases. So if you put a lot of carbon dioxide into the air and methane and all those other gases, you can work out how much energy is being trapped, and the energy balance model will suggest that that's the influence on temperature. So you can see that the solar effect is up and down, and there's a bit of a contribution here, but it's not producing anything like enough to create the global warming. So that's on the basis of fundamental understanding of the energy balance. You can try and do this in a different way by using big climate models. Now by climate model I mean a big computer program, a similar sort to which the Met Office uses to do the weather forecasts. So you write down all the equations that describe the flow in the atmosphere and the physical processes, and you code them up in a way that can integrate in time and study changes in the climate. And there's 2 plots here. Both of them show a black curve, which is the observed global mean temperature. And then the coloured curves are estimates from these global climate models. And the bottom one includes only natural forcing, so it's only got in the volcanoes and the sun. And you can see that it's not doing badly. I wish I had a pointer, sorry, I'm trying to use this thing. It's not doing badly over this period here, but when you get into the latter half of the 20th century, it just can't do the business without putting in the greenhouse gases. So in an overall global average sort of sense, we can explain quite well what the contributions are to the temperature and how much the sun contributes. In detail, however, it's much more difficult, and you can see that there's lots of little, there's lots of little wiggly, faint wheels on there, and each of those is a different run of the climate model from a slightly different starting position. And these are giving estimates of the noise in the system. So it's a complex, non-linear system. It's doing all sorts of wonderful things off its own right. So we don't know which precisely one of those very thin lines that the climate is doing, but on average, we can see that it's going to be doing something like this, and the uncertainty in our estimates is given by the spread in all these little coloured wiggles along here. So you might think, okay, right, she said now, the sun doesn't cause global warming, end of story. I'm afraid you can't escape quite that easily, because there's all sorts of other interesting things going on. So on the right hand there, again, is a picture of the global effects and the contributions of ENSO, that's El Nino, which is a large contribution to global tropical sea surface temperatures, which contributes to global temperature change, and the other factors I've already described. But on the left, instead of having a global average, we're looking at maps over the surface of the Earth. So you can see at the top here we've got the El Nino. Whoops. We've got the El Nino with a big warming in the tropical sea surface. We've got the volcanoes, which are sort of cooling almost everywhere, mostly over the tropics. This is anthropogenic, so this is greenhouse gases, and most of the warming is over northern hemisphere land surface, but it's warming everywhere. But then the solar cycle changes, interestingly, are pretty much zero in the tropics, but have some signal in what's a mid-latitude, so 40 to 50 degrees each side of the hemisphere. So that's quite an interesting thing to think about why that might be. And here's another picture of estimate of what the solar cycle effect is doing. This, confusingly, is low sun minus high sun, so it's the opposite way around to the picture I just showed you. But it's suggesting that when the sun is less active, we get colder weather over here and warmer weather over Greenland. And this is a well-known pattern of variability in climate called the North Atlantic Oscillation. So the regional effects of the sun are much more complicated and different than just the sort of global average picture. And before I go on any further, I'm just going to make sure you know about the temperature structure of the atmosphere. So if we look at the lower atmosphere here, temperature's decreasing with height for about 10 to 12 kilometres. This is in the region of the atmosphere called the troposphere, and you can see it's where all the weather is. That's Mount Everest there to give you a scale. It's where all the weather and the clouds are and everything else. But above that, we've got the ozone layer. And because there's ozone and photochemistry going on, the temperature increases with height in what's called the stratosphere. And what I'm going to talk about now, I'm going to mention the stratosphere and the troposphere. The stratosphere is just sitting above the troposphere, and it's where there's warmer temperatures. And now we're going to look and see what happens in response to the sun. So this, we did this a few years ago, and what we found is that what the sun does is heats the low latitude stratosphere, which is what you might expect. You've got more solar radiation coming in, it's going to be more in the equatorial regions, that's where the heat is going to go. But then we found in the troposphere, there's bands of warming in mid-latitudes, which is not what you'd immediately guess. But it's entirely consistent with that map I showed you just now with the warming at the surface in mid-latitudes. This is the same thing but for winds. Now this is the westerly winds going around the globe. This is the average situation. So each of those reddish spots is like a jet stream blowing around the globe at near the tropopause from west to east. I'm afraid I've got not height on the vertical axis now, but the meteorologist's favourite unit, which is pressure, which is telling us about the mass of the atmosphere rather than the height, but it's still going upwards. And this is showing the difference between solar max and solar min in the zonal mean zonal wind. And what you can see is blue means negative and red means positive. So when the sun is more active, what's happening is that the jet is actually slightly weaker, and it's also slightly shifted towards the pole. And that's happening in both hemispheres. The southern hemisphere is more complicated because there's a sort of double jet. But so that's it's suggesting again that you'll see the biggest effects in mid-latitude. So if you're somebody who's got their weather station in Scotland in your garden, and you've been seeing 11-year solar cycles, over decades, or have to be several decades, perhaps you're not quite as batty as people have been calling you, because actually you're likely to get a bigger signal in those regions than you are in other areas of the globe. So now we're just going to look and see why that might come about, and to do that we need to look at the solar spectrum. So the picture on the top there is a spectrum of the sun. You can see it's going through the ultraviolet, the visible and the infrared, peaking in the visible. And down the bottom here we have quite an old estimate. This is a 1991 estimate of what the sun was doing over the solar cycle. Now the blue and yellow thing there is giving us the 0.1% that we get in the total irradiance that I showed you in that colourful plot from satellites. So it's quite a small variation, and that reflects what's going on in the visible. But you can see as you go into the ultraviolet, the changes are much larger. So we're going from sort of just 0.1% to 1% to 10% to 100% by the time you get down to about 100 nanometers. The solar energy is doubling from solar max to solar min. So you think, oh, that's interesting. If there's a lot more UV coming out, how's that going to affect the atmosphere? So what we did was, that's the observations I've already shown you. We put some changes in ultraviolet radiation into one of these climate models, and we looked to see what happened. Now this model here, you can see its jets are too strong, but it's got the right sort of pattern. And the response is too weak, but it's got the right sort of pattern. And that's interesting because the only change in that experiment was changes in ultraviolet radiation, and the sea surface temperatures were fixed, so it had to be a sort of top-down effect. And then we thought, well, how are we going to understand that? Understanding these models is almost as complicated as understanding the real atmosphere. So we sort of sized down the problem, we stripped away the model, we got something much simpler, and we looked to see what happened in this very simple model. We just banged in some heating in the stratosphere and looked to see what happened. And we got a much stronger signal. Down here you can see this is just one hemisphere now and just one jet. Again with the weakening and shifting, just in response to heating in the stratosphere, lower latitude stratosphere. And you can see how this evolves. We switch the heating on at the beginning here, and so you see the effect starts off in the lower stratosphere, but then after about 50 days it's dripping down, and you can see this effect building up in the troposphere. So something's happening that starts at the top, here it goes again, and then it's sort of swept downwards into the lower atmosphere. And I haven't got time to go into the mechanisms now, but let's suffice to say that, I put all these things in here, what we think is happening, I say we, this is Ida Simpson, who was a student of mine quite recently, changes the temperature in the stratosphere, which affects the winds up there, and that affects the way that these weather patterns influence the momentum flux in the atmosphere. And when you've changed the momentum fluxes, that has an effect on these overturning circulations in the atmosphere, which then affects the weather near the bottom, near the surface. And when you've affected the weather near the surface, you then affect these waves again. So you've got a sort of feedback loop. And so our hypothesis is that the sun's influence on climate is top-down, but it depends crucially on what the UV is doing. So I showed you earlier the source satellite measures of total irradiance had come in rather lower, the changes to come in rather lower, the absolute value had come in rather lower than what had previously been estimated. Well, the source satellite also has solar spectra, and here's some of its measurements in the ultraviolet. We're going up to 300 nanometers here. So these values, red and blue, these are ones like the one that I showed you, the 1991 change in spectrum. These are the ones that are coming out of this source satellite, and you'll notice that it's log scale there, so actually they're about a factor 6 or 7 larger over the period, estimated over the period 2003 when the sun was quite active to 2008 when it was not very active than previously thought. This is really interesting because you see, with our idea, we want lots of UV to change the stratosphere so we can have big solar effects going on down below. So I haven't got the end of this story yet. What we're doing at the moment is we're putting in these different amounts of UV into a model that's looking at stratospheric ozone, which is all part of the story. and also for which we have independent measurements. And you don't need to look at all these panels in detail, but what they're showing is changes in ozone in response to each of those different spectra. And you can see they look very different. Some of them have got negatives at the top, some of them are much bigger at the bottom. So what we're doing at the moment is looking at these estimates of ozone, comparing them with satellite measurements of ozone in order to try and deduce what we believe about the solar spectrum. So it's rather a nice sort of backwards way of looking at it. So, a few minutes late, does the sun's energy output vary? Yes, definitely. Is there any evidence for a solar influence on climate? Yes, it's globally small, but regionally a bit bigger. Is the sun responsible for global warming? No, but it's probably contributed to the first half of the 20th century. Can we explain solar signals in climate? Globally, probably yes-ish, with some error bars. Regionally, it's a really exciting area of research to be working in. So just to finish off, I would want to include a quote from Sir William Herschel, who was interested in this topic. He wrote a paper in 1801 in Phil Trans, in which his sunspots were his measure of solar activity and his meteorological parameter was the price of wheat on the London Stock Exchange. So you can imagine his statistics were a little bit iffy, but he found it very difficult to work this out. But he thought that more or less light and heat from the sun might produce a great change in the seasons. Now, he didn't have computer models or any of these other things that we've got, but he was a very good scientist. He could design at least thought experiments. When many things which are already known to affect the temperatures come to be properly combined with the results we propose from solar estimates, we may possibly find this subject is less intricate than we might apprehend. So I think William Herschel, were he to be listening to me today, might be rather horrified to find actually it's still just as intricate and just as fun and just as exciting as ever. Thank you very much.